So let us start today's session. Today's session is lecture 1 under Boolean Algebra. Boolean, Boolean Algebra. So it's a binary algebra. Base is 2. So the variables in Boolean algebra can take two values. Let us say if x is a binary variable, x can take either 0 or a 1. Right? Either 0 or a 1. Right. So before getting into the details of Boolean algebra, we should learn one important theorem in our Boolean algebra. That is duality theorem or duality principle. Duality theorem, duality theorem, or duality principle. Right. One of the fundamental theorem. If you are comfortable with the duality principle or duality theorem, then the Boolean algebra equations, postulates, etc., will be easier. Okay. So duality theorem. So let us see what is a duality theorem and how to identify the dual of a given function, given expression, given variable, given constants. Right. In binary, we are having two constants, 0 or a 1. Okay. So suppose we have a function, binary function f. Right. Its arguments are binary variables, that is a x, y, z, etc. Okay. N number of variables, comma. There will be or sign in the algebra. There will be and sign also. And sign is represented by a dot, right? Along with you'll have constants. They are zeros and ones, right? So any function, any expression will be containing any one of these, right? Not all. Sometimes x, y, z only. Sometimes x, y, z or and signs. Sometimes zeros and ones will come in the expression. Okay. So if the given function contains these items, these arguments, variables, then or operator and operator, then constants. Okay. Then it's dual function. I will call it as f subscript t, a dual of that function. Ft is the dual of f. Dual of f is defined as, so if you're taking the dual of a given function, you should not change the variables, okay, the form of the variables, or simply the variables will appear as such, no change for them. Okay, you should not replace or substitute your variable with another variables or its complements, etc., not change for the variables. But your or sign will be changed with its dual operator, that is AND operator. Your AND sign will be replaced with its dual operator, it is OR operator. Then the constants, zeros, will be replaced with its dual, they are ones. And the constant 1 will be replaced with the zeros. So that is what is a duality theorem is. You are given with an expression, then its dual can be easily identified by keeping the same variables, same form of the variables, replace and sign with or sign with and sign, and replace your constants, zeros with ones and ones with zeros. Okay. Suppose you are having complements, x bar, y bar, z bar, then you should make use of same form, complement form. You need not replace them. Okay, so variables or its complements will appear as such, no change. But and or signs will exchange. Zeros and ones also will exchange from true form to dual form. Okay, and one more important statement from duality principle or duality theorem is that if this is important, okay, we will be using this throughout of our course. This is important. If if an expression is valid, an expression is valid, okay, valid, then, then, then its dual expression, dual expression, expression is also valid. Expression is also valid, valid. A valid expression will give you another valid expression if you're taking the dual. Okay. So if an expression is valid, then its dual form is also valid. And this will help us while simplifying the Boolean functions. Suppose you are given with a function and you are not able to simplify that. You tried your level best to simplify that, but you couldn't. Then, if you are taking the dual of the given expression, then you may be able to simplify that expression into a small expression. Then, if you're taking the dual of that small expression again, then you will get the simplified expression corresponding to the actual given expression. Expression 1 is given, right? You try to simplify this, but you couldn't. Then you take a dual of that, okay? You took the dual expression of that expression. Then you got a second expression, and that you could simplify it quickly, right? And you have that expression here. Then if you're taking dual again, okay, dual again, you will get the actual required result here, okay? So that will help you while simplifying Boolean expressions. Given expression, you are not able to make it, then take the dual, then you may be able to simplify it quickly, then take the dual of your simplified expression again, you will get the simplified expression corresponding to the original given expression. Okay, so duality theorem or duality principle is very, very important. Right? Is that clear? Duality principle or duality theorem? Is that okay? Then any queries? If clear, please type yes in the chat box so that I can move to next topic. Right? Is that okay? Right? This statement is important. Right? You can easily remember that. Valid expression will give you valid dual expression also. Right? Then if your original function and the dual functions are same, okay? If your original function, this one, and dual function, the second function, both are same, and then we'll call it as the function f is a self-dual function. Self-dual function. Okay, self-dual function. Right. If the function is equal to the complement of the dual function, right? Then we'll call it as an orthogonal function. Orthogonal function. Orthogonal function. Okay, it's just a statement, right? If both are same, is self-dual property, having a property of self-duality. Then if they are related through complement operation, f and ft, we'll say that they are orthogonal each other. Orthogonal function. F is orthogonal function, right? So that was my theorem number 1 in Boolean algebra. Strong principle, duality principle. Okay, right. Then the second theorem is a familiar one. That is what is called De Morgan's law. De Morgan's law. De Morgan's theorem or De Morgan's law. This you are familiar with. It has two statements, statement number 1 and statement number 2. First statement state that the complement of a sum, complement of a sum is equal to product of individual complements. Okay. If you're taking the complement of a sum, and that is same as product of their individual complements. Here A, B, C, D, etc. are Boolean variables. So you took the sum of the all variables, then you took the complement, and that is same as the product of individual complements. So sum to product relation. Similarly, the second statement is if you're taking complement of a product, complement of a product, that is again equivalent to or equal to sum of individual complements. Sum of individual complements. Okay, very simple and easy to remember, and you are quite familiar with this. De Morgan's law or De Morgan's principle. Okay, so if you are comfortable with these two theorems, we'll move to Boolean algebra. First, we'll discuss a few postulates and few simplification theorems, few identities, okay, that everyone knows. Okay, so let us go through that quickly. These two are clear? Yes. Shall I proceed with Boolean algebra? Right. These two theorems we will be using throughout of our course. So please try to understand this De Morgan's law and duality theorem. Okay, all right. Okay, so I'm moving into Boolean algebra. Simple postulates we will discuss. Okay, the first one is one dot the variable a will be, what is the value of 1 dot a equal to a itself, right? A itself. So if you're taking the dual, what's the dual of left hand side here? 0 plus dot will become plus variable not change, right hand side variable not change. So if you're adding a 0 with a variable, you will get the same variable, 0 plus a equal to a, right? Similarly, a dot a will be, if you're taking the product with the same variables, you'll have a itself, same variables. And I'm not going to the proof. Proof is it's direct. If a equal to 1, 1 dot 1 will be 1. If a equal to 0, 0 dot 0 will be 0. So a value will be on the right hand side. And if you're taking the dual of that, you'll get a instead of or, instead of and, I should write or equal to right hand side a itself. Okay, so that is also valid. Right. Then I will take another expression, that is a plus a bar. What is a plus a bar? A can be 0, then a bar can be, complement will be 1, so that result will be 1. A can be 1, then a bar will be 0, then also the result will be 1. Right, so irrespective of the value of a, the result will be 1. So a plus a bar will be 1. So what is the dual of that? If you're taking the dual, a will be a itself, no change while taking the dual, or will become and sign, a bar, no change, right? No change for variables and their complements. Right hand side, 1 will become, dual of 1 is what? 0. So a bar dot a or a dot a bar will be 0. That everyone knows. Simple postulates in Boolean algebra. Okay, right. Okay, then let us take one important simplification tool that we'll use extensively in while simplifying Boolean algebra. That is a plus a bar dot b. What is this? What is the simplification of a plus a bar b? A plus a bar b. No problem. If you are not able to recall it, just take the dual. What is the dual of this? A dot a bar will be same a bar, and this dot will become or here dual of this b, that's equal to, so a dot a bar you can split into two, a dot a complement plus a dot b equal to, so we said a dot a bar will be always 0, right? A dot A bar is 0. So this is 0. So that will become A dot B itself, right? Then if you're taking a dual of this, you will get the original expression. What is the dual of A dot B? A or B, right? So A plus A bar B is simplified as A plus A bar B is simplified as A plus B, right? And that you can easily remember. That also requires, right? While simplifying Boolean expressions, A plus A bar B can be simplified into A plus B, right? Then let us take another simplification. Let us take the product of A plus B and A plus C. What will be the result? A plus B dot A plus C. What is the result? If you are not able to identify the result, no problem. Let us take the dual. Let us apply duality principle. Duality principle. So if you are taking the dual of this, you will get A dot B, right? Or will become and. This and will become or, right? Again, or will become and, right? So AB plus AC. So A is common. So A dot B plus C. So this is equal to the dual expression simplifies to A dot B plus C, right? So if you're taking dual of that, dual of this, okay, you will get A dot will become plus. There is a dot here, so plus, and B or C will become B dot C. So A plus B dot A plus C is nothing but A plus BC. Or the other way, A plus BC can be expanded as A plus B dot A plus C, or A plus B dot A plus C can be simplified as A plus BC. Similarly here, A plus A bar B can be simplified into A or B or A plus B. Similarly, A plus B can be expanded as A plus A bar B, right? Okay, so these two you should keep in mind. Simplification. Okay, right. So we have one more term that we are going to use in simplification of Boolean algebra. That is literal. 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 Okay. So from a given Boolean expression, and if you're simplifying that expression, you will get a simplified expression, right? To check whether your expression is simplified or not, the method is to count the number of literals. If the number of literals are less, that implies your expression is a simplified expression, right? Compared to the number of literals present in the given expression, if your simplified expression have less number of literals, then we will say that the second expression is simplified expression. So we should understand what is a literal is. Let us take down the definition of a literal. Literal is defined as the each occurrence, each occurrence of a variable in its true form, in its true or complement form, true or complement form is called a literal, right? Each occurrence of a variable in its true form or complement form is called a literal. You please note this word each occurrence, right? So let us go back to the earlier slide. Here, left hand side, I have a plus a bar b. Each occurrence of a variable or its complement is called a literal. So I have one literal here. A bar is also another literal. B is also another literal. So I have three literals here. whereas your simplified expression contains only two number of literals. So we'll say that second expression is simplified one. Right hand side is simplified expression. Similarly here, 1, 2, each occurrence is a literal. So a is appearing again. So I should count it as a another literal. Each occurrence of a variable is called a literal. Okay, so 1, 2, 3, and 4. I have four number of literals here on the LHS. Right hand side I have 1, 2, 3 number of literals. So right hand side is a simplified expression. Okay, so as the number of literals are less, the expression is getting simplified more and more. Okay, the least number of literals will imply the expression is most simplified. Okay, most simplified. So that is a literal. Okay, is that clear? These simple postulates and simplification, right? Is that clear? Any queries, any doubts? Shall I move to questions? Then yes, shall I move? Okay, so let us have another question based on this. Okay, question number one. Simplify the given expression x plus p dot x plus q dot x plus r. Simplify the given expression x plus p dot x plus q dot x plus r. Four options are given: x plus p plus q plus r, x plus p q r, x dot p plus q plus r, then x p plus q plus x r. Four options. So what is your option A, B, C, D? Four options are given. Right, it will be second option. So this is A plus B dot A plus C form. So that will be A plus BC. So that will give you X plus PQ. A dot with again X plus R. This is also of the form A plus B dot A plus C. B is my PQ. So that simplifies into A plus BC. A is X, X plus BC, B is Q, P dot Q is P. This is my P. And C is R. So A plus B dot C. C is R. So X plus PQ R. Right. So what if the given expression is, let us say, X plus P dot X plus Q dot X plus P complement? What will be the simplified expression corresponding to this? X plus P dot X plus Q dot X plus P complement. This will be X. This is A plus B dot A plus C form. So these two will give me X plus P dot Q. Again, another X plus P complement. That will give me X plus, this is my B, BC, C is my P complement. So P dot Q dot P complement. And we know that the product of P and P complement will be 0. That will give me X. Right. So please keep this expression in your mind. Right. This one and this one. Okay. All right. So let me have another question. Did you copy this? Last slide, question number one. Then yes. Okay. I'm moving to question number two. Simplify the given expression. Simplify the given expression. A plus A bar B plus A bar B bar A plus A bar B plus A bar B bar C. And you are given with four options. It's A plus B, A plus B plus C bar, A plus B plus C, and A plus B bar plus C bar. Simplify the given expression A plus A bar B plus A bar B bar dot C. A plus A bar B plus A bar B bar C. Right? Is that one? Right? If you are not able to solve this, you are confused, no problem. Let us take the dual of the given expression. Dual of this. What is the dual of this expression? It will be A dot. This is actually dot A bar B. So A bar plus B dot with A bar plus B bar plus C. So if you're taking A into the bracket here, so we'll get A dot A bar plus A dot B, protect with A bar plus B bar plus C, taking the dual. So this will be 0. So we'll get AB dot A bar plus AB dot B bar plus AB dot C. So again, we know that this protect A dot A bar will be 0, B dot B bar will be 0. So I will end up with ABC. Then take the dual again. You will get the simplified expression here. Dual of ABC is A plus B plus C. Right? The duality principle will help you. Okay. Or if you would like to simplify it using the expression A plus A bar B form, that also you can go for with that. So A plus A bar B, first two terms will be A plus B. Then you have A bar dot B bar dot C. Right. Then first term A plus third term A bar B bar C plus another term B. So this is of the form A plus A bar B. This together is my B. So I can write it as A plus A bar B form. So A plus B. So A plus my B is B bar dot C plus another B here. So this will be again A plus B I'm writing here, then B bar C. So this is B plus B bar C form, A plus A bar B form. So this will be A plus A bar B, or B plus B bar B will be B plus C. So I will end up with A plus B plus C. Right. So you can either go proceed with the duality principle, or you can directly simplify using the expression A plus A bar B equal to A plus B. Both are equivalent. Right. So if I am extending that question, did you copy last slide? Then copied. Then okay. Right. If I'm extending that question with n number of variables, let us say A plus A bar B plus A bar B bar C plus A bar B bar C bar D plus A bar B bar C bar D bar E plus etc. And what will be your solution? It is n number of terms, etc., etc. Right? We had these three terms. We got A plus B plus C. If you are adding one more term, you will get A plus B plus C plus D. And one more variable here, a plus b plus c plus d. So if you're adding n number of variables, you can simplify this using the same principle what we have discussed here, either duality theorem or direct method. Both ways, you will get the simplified expression as a plus b plus c plus d plus e plus etc. up to n number of terms. Okay. So from a third term, you will get a C. Fourth one, you will get a D term. Then the fifth term, you will get a single E term. Right. So you can try this as your homework, similar to what we have discussed. Okay. Right. Simplification of Boolean algebra. Okay. Right. Copied. Then shall I move to next topic? Yes. Okay. Okay. So we have half an hour more. So let us have a short discussion about min and max term. Min and max terms. Okay, min and max terms. Then we'll come back to simplification of Boolean algebra again. Okay, before that, let us finish it. Min and max terms. Okay, so to explain about min and max terms, or simply min terms and max terms, let us consider a system with let us say three number of inputs. Okay, you're having a system or logic circuit, let me call it as L. It accepts three inputs, and these inputs are, let us call them as X, Y, and Z. And that circuit, that combinational circuit or combinational logic, produces a function f output. Of course, output will be proportional to the inputs. They are X, Y, and Z, right? It's a combinational circuit that produces one output. Output is also a binary function. Inputs are binary variables X, Y, and Z. Okay, so X, Y, Z can take different values. Different in the sense either 0 or a 1. So if X and Y are variables, X, Y, and Z are three variables, right? It can take a total of 8 different combinations, because individual variables can take two values, either 0 and a 1, and we have three numbers, so possibility is 2. We're having three variables, so we'll have 8 combinations together. Okay, so let me write those combinations. They are, I'm keeping the progressive order, 000, then 001, 010, 011, 100, 101, 110, and a triple one, right? And my aim is to represent this function f using either min terms or using max terms, right? I'm trying to represent my function using either min terms or max terms, two different ways, right? Because function f is a binary function. It can take a value of 0 or a 1, right? If it is taking a 0 value, I would say that I am expressing the function using max terms, 0 corresponding to. If function f takes a value 1, I prefer the expression using min terms. Okay. So basically, to express a given function or output of a given logic gates or a logic circuit or a combinational circuit, we have two different methods. Either you can specify all combinations at which your output will be 0, right? You can specify x, y, z values that will give you f equal to 0, right? If f is not equal to 0, by default, f will be 1 because f can take only two values. Similarly, if you're expressing f in terms of inputs x, y, z, you can specify a set of values for x, y, and z so that for that particular combinations, your function f will give you a logic 1. That is min terms. Then equivalently, if f is not equal to 1 by default, f will be equal to 0, right? So effectively, if you are expressing function using min or max terms, you are specifying the condition on f and inputs. If you are specifying with min terms, you are specifying that for those particular combinations, f will be equal to 1. If you are specifying the function using max terms, you're actually saying that for this many particular combinations of my xyz inputs, my function will be 0. And you'll be confused a little bit. Let us clear it by explaining using a truth table. Okay, so this is your function, and I have xyz inputs. Okay, xyz inputs, and if you're providing different inputs, you will get different outputs. Okay, and suppose you're going to design this logic, right? And you have a clear-cut idea that if x, y, z are zeros, your function output should be, let us say, 0. Okay, that is your choice. Okay, if all inputs are 0, my function should be 0. If my inputs are 0, 0, 1, then my requirement is, let us say, you are going to design that circuit. So our requirement is 1. You can assign any values, but I'm going with a 0, 1, 0, 1, 0, 1. Right. So if it is a 0, 1, 0, where our requirement is output should be 0. If x equal to 0, y equal to 1, and z equal to 0, my f should be 0, or the other way, the circuit should produce a logic 0 at the output. If it is a 0, 1, 1 condition, my output should be 1. 1, 0, 0 output should be 0. 1, 0, 1 output should be 1. That is our requirement. Okay, you can assign any value for f corresponding to input combinations. 1, 1, 0, I'm assuming it as f should be equal to 0. And 1, my requirement is output equal to 1 if x, y, z are 1, 1, 1. Okay, so these are my requirements. Then I should logically express the function f, right? I can use either min terms or max terms. So before that, I should define what a min term is or what a max term is. So let us define first the min term. Okay, min term. Please listen carefully. This is heart of the subject, min and max terms. Okay, that will help us while discussing combinational circuits, multiplexers, sequential circuit, etc., etc. Everywhere we are going to use min and max terms. Okay, so this is important. I'm requesting your attention for at least 5 minutes. Okay, so please listen carefully. Right, it is easy to understand. If you're not listening properly, I have to repeat it. That will take more and more time. Okay, so please listen carefully. So I have one column corresponding to min term. Okay, another column corresponding to, let us say, max term. Okay, don't worry, we'll discuss what a min term and max term is. Okay, so this is my function f. Okay, so let us define min and max terms corresponding to each and every combinations. Then we will express the function f using either min or max terms. Okay, so min terms are very simple. Min terms are product terms. Okay, min terms are product terms product of x, y, z, or x bar, y bar, z, or x bar, y, z, etc., etc. And the property of that product term is that that product term always should return a logic 1, right? So this should return always a logic 1. Okay. So corresponding to my first combination, right? I should write it in product, and that product should return a 1. Product in terms of x, y, z. Then that product should return a logic 1. Then I have only one option. It should be a product. All are 0. So their complements are 1. So x bar will be 1. Okay. Y bar will be also 1. Okay. Product with a z complement. Right. Since x, y, z's are zeros in the first row, the product x bar, y bar, z bar will be 1 dot 1 dot 1, and that will give me a 1. Right? So that is a product term corresponding to first combination. And I should identify that particular min term. I'm going to identify that min term using an index and a small letter m corresponding to min term, right? Small letter m. So I will write it as small letter m. Okay. And I will put an index. Index is decimal equivalent of my first combination. What is that? 0. M0. M0 implies x bar, y bar, z bar. Very simple. Then with respect to the second combination, I should get a 1 corresponding to x0, y0, z1. Then I should write it as x bar, y bar, and z. So the combination's decimal equivalent is 1, so I should write here 1. Okay. Third row, I should get a 1 corresponding to the product. So x is 0, so x bar should be 1. Y is 1, so y itself. Z is 0, so z bar equal to decimal equivalent of 0, 1, 0 is 2. So this is M2. M for min term and 2 for the respective combination. Okay. 0, 1, 0 is decimal equivalent is 2. So similarly, fourth row, I can easily write it as x bar y z equal to m3. Then fifth row, x y bar z bar equal to m4. Okay. Sixth row, x y bar z equal to m5. Then seventh row, x1 y1 z0 equal to my m6. Then all ones implies x, y, z equal to decimal equivalent is 7. So M7. So for a 3 variable system, I'll have 2 power 3, 8 combinations. So I have a maximum of 8 number of min terms. 8 number of min terms. Right. So I'm getting into max term. Max terms, as we said, max term will give me logic 0. And that max term should be a sum term. Okay, sum term. So look at the first combination, 000. We should express a sum. That sum should be give me a 0 value. So the best possibility is x plus y plus z. It's a sum term that will give me a 0. And that is expressed using a capital M. It's a max term, capital M. And the index is same, decimal equivalent of 000. Similarly, second case, x plus y plus z is 1, so sum should return a 0, so I should add z complement, and that will be m1. Then x plus y bar plus z, third row, that is my caps m2. Then x plus y bar plus z bar, that is my caps m3. Then x bar plus y plus z, that's my caps m4. Then x complement y plus z complement will give me m5. Then x complement plus y complement plus z will give me m6. Then x complement plus y complement plus z complement, because all x, y, z's are 1, okay, will give me m7. Okay. So I have defined my min and max terms. Okay. Right. Then I'm going to express my function f. function f using min or max terms. Okay, so first I'm going to express my function f of x, y, z using min terms. Okay, min terms. Min terms are those terms that will return a logic 1. So I'm going to express a function f that returns a value 1. What are the conditions to f equal to condition for f equal to 1? Okay, so f equal to 1. So look at this truth table. F is 1 here, f is 1 here, here, and here, right? So if combinations are 001 or 011 or 101 or 111, then function f will be equal to 1, right? So I should take minterm 1, minterm 3, minterm 4, minterm 7. Sorry, minterm 5 and minterm 7. So any these combinations, either 001 or 011 or 101 or 111, my function will be 1. So I can easily express my function f equal to, I should take the respective minterms. First minterm is this one m1. M1 is x bar, y bar, z. Or if x equal to 0, y equal to 0, z equal to 1, my function is 1. So logically, I can express it as x bar, y bar, z. That is a one condition, right? And there is not only one condition. I have few more conditions. They are, I have a 1 here for f. So 0, 1, 1, 0, 1, 1 corresponding to m3 x bar y z. So I should take x bar y z plus. Another one condition is here corresponding to m5, small m5, x y bar z, x y bar z. So x y bar z plus one more condition, last column, here it is 1. So 111 x y z or m7. So this is x y z. So I'm converting into min terms because I am not ready to write always x bar, y bar, etc., etc. So I am going for short notations. 001 corresponding to m1, min term 1. This is m3, x bar, y z is m3. Look at this, x bar, y z is m3, right? So I'm writing sum of m3, then m5, then this is m7 because it is 111, m7, 101, 5, 0113, 001, 1. So m1, m3, m5, m7. Then it's a continuous sum. So I'm going to use a simple sigma of m1, comma, m3, comma, m5, comma, m7, right? Always I'm not ready to write m again and again, so I will go for only indexes sigma 1, 3, 5, 7. So the function f of x, y, z is represented as sigma 1, 3, 5, 7 using midterms. And we'll call this representation as is it sum of individual products or product of individual sum? It's sum of individual products, right? So this is a SOP form, sum of individual product, sum of individual products, right? SOP form. Okay, very simple. So the function can be expressed as f of x y z equal to sigma 1357. 1357 are nothing but those combinations. Please listen. Those combinations at which function equal to 1. 1, 001 is 1, 011 is 3, 1, 3, 101 is 5, 5, 111 is 7, right? So 1357. So those indexes present in the sigma representation will give you the corresponding combinations of x and y, x, y, and z or inputs. Corresponding to that, your function f equal to 1. All other combinations by default function will be 0, right? And this is the one of the method that is sum of individual product or SOP form. Similarly, you can express using max terms also. As I said, that will give you function value corresponding to your inputs. Those input combinations corresponding to that function will be 0, right? Okay, so similar to this, if you're going to express function f, you should identify the condition for 0. Look at the truth table. Here you're having a 0, right? Here also you're having a 0. Here also function should be 0. Here also function should be 0. And max terms will give you individual 0 terms. Okay, so we have max terms. Individually they will be 0, right? If any one of them equal to 0, your entire function will be 0, right? So I should express that function as a product of max terms, right? Product of max terms. The max terms are, first one is x plus y plus z. If x, y, z all are zeros, look at the truth table, all are zeros, my function should be 0. So x plus y plus z, that is my capital M0. Then if x0, y1, z0, x0, y1, z0, then also my function is 0. So I should take a product, right? Product. Any one of this term equal to 0, the entire function is 0. So product of caps M2, right? Caps M2. X plus y bar plus z. X plus y bar plus z. X plus y bar plus z. Next, the other term is caps M4. Look at the table. Here it is M4. X bar plus y plus z. X bar plus y plus z. The last term is capital M6. Look at the truth table. M6 here. Function is 0, 1, 1, 0. So x bar plus y bar plus z. X bar plus y bar plus z. Right? So converting into indexes, this is caps M0. This is caps M2. This is caps M4. Right? This is caps M6. It's a product. Product. So I will make use of pi symbol. It's a continuous product of what? M0, comma, M2, comma, M4, comma, M6. Again and again, I am not ready to write capital M. So I will take only indexes pi of 0, 2, 4, and 6. Function f. So all these conditions, all these combinations, 0, 0, 0, 0, 1, 0, 0, 1, 0, then 1, 1, 0, 0, then 0, sorry, 1, 1, 0, 6. All these combinations of x, y, z, x, y, z, your function will be 0. And this is product of individual sum. So it's a POS form. Product of individual sum form. POS form. Okay, so the same function can be expressed two different ways. The same function I'm expressing here, you can express it as f equal to sigma 1, 3, 5, 7, or f equal to pi of 0, 2, 4, 6. Right? And please note that the indexes present in sigma term won't be present in the pi indexes, and vice versa. Okay, so the same function f can be expressed differently by using either min terms or max terms. Max terms continuous product, because if any one product is equal to 0, the entire function is 0, and then the terms are 0. And SOP form, sum of individual products, at least one product is equal to 1, then the function should be equal to 1. So it's a sum term. So basically, you can express your function using two different methods, SOP and POS. Okay, is that clear? This is fundamental. This is required throughout the course. All right, any queries, any doubts? All right. So next class we'll move to consensus theorem. That is an interesting tool for simplification. Before that, we have just now we have finished min and max terms. After consensus theorem, we will get into logic gates. Okay, number of functions possible using two binary variables, using three binary variables, everything we'll discuss in between. Then we'll get into logic gates. Okay, is that clear? Min terms and max terms, right? We'll define min and max terms of individual logic gates and or not NAND, XOR, XNOR gates. What are the min and max terms corresponding to each logic gates? Any other queries? Right? If
Sir,
yes,
sir, F equal to 1 in a max term, you say the geometry.
right. Okay. So look at this two table. Uh, if you are writing f equal to 1, function f equal to 1, you're having 1, 2, 3, 4 combinations. Okay, f equal to 1. So that f equal to 1 corresponding to combination 1 here, 001, combination 3 here, combination 4 here, sorry, combination 5 here, then 7. Okay, so f equal to 1 condition can be expressed using min terms. Okay, f equal to 0 conditions can be expressed using max terms. And your question is f equal to 1 condition can be expressed using max terms or not. Okay, so it is not about f equal to 1, f equal to 0 condition, it's just f. So the function f that can be expressed using max terms only, that is this representation, product of max terms, caps m0, m2, m4, and m6, right? It's not like f equal to 1 condition. It's a condition for f, right? It is valid for all combinations, all three, all 2 power 3 combinations, all 8 combinations. And similarly, the same function can be expressed using min terms also, but that should be a sum term. So m1 plus m2 plus m5, sorry, m3 plus m5 plus m7. So it is not like f equal to 1 or f equal to 0. It's simply f. We are talking about this column. Irrespective of your combinations, you should specify f. So according to the combinations, you will get either 0 or 1 at the output f. So you can express using min or max terms. Okay, Princey.
Okay, sir. Okay, thank you.
Right. Any other queries? If no other queries, we will wind up today's session. Next class, we'll continue from simplification of Boolean algebra using consensus theorem. Okay. I think min and max terms are clear to you all. If not, you please ask me to explain more. I don't have any problem because this is most important. Okay, if you are clear with this, I can go with other topics very easily, right? I think it's clear to you all how to express a function using min or max terms from its truth table, observing its truth table. Okay, we took a 3-bit example. Can explain minus 1 decimal 2's complement. Okay, minus 1 decimal in 2's complement representation, right? Okay, minus 1 decimal in 2's complement representation is just a 1. Okay, so only one bit MSB is this. Okay, so 1 in 2's complement representation means the number is negative. And before, right, okay, we'll take that. Before taking the magnitude, you should take the 2's complement of the representation. 2's complement of 1 is nothing but 1 itself, right? So this is actually minus 1 decimal. Okay, and we said that if you are extending the MSB bit, let us say 1 1, you are extending one more MSB, right? MSB was 1 here, so I'm extending to one more MSB. 1 1, this is again number is negative. I should take a 2's complement before obtaining its magnitude. So 2's complement is nothing but should travel from right to left. Repeat until you're observing a 1, then complement the individual bits. So this is also nothing but minus 1 decimal. So if you're extending one more, triple one, this also will give you 001 2's complement, will give me minus 1 decimal. So if you are extending 15 MSBs, you will get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and a 1. we'll get same minus of 2's complement of this will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and a 1 because I should start from right extreme, should move towards left. Repeat up to I'm observing a 1, then complement all other digits. So this is nothing but minus 1 decimal. So minimum number of bits required to represent a minus 1 is minus 1 decimal in 2's complement representation is only 1 bit. And if you're extending that to n number of bits, the value will remain minus 1 decimal. Aditya, is that clear? Done? Okay. Right. Any other queries? So shall I wind up? Can you explain digits to represent a minus 254 using 2's complement? Okay, that we have did in the class, minus 254. Okay, so to represent a minus 254, you should identify the binary pattern of 254, right? Binary pattern of 254. To identify that easily, you can take an example. If you're having 4 digits, 1, 2, 3, 4, it's a decimal 15, right? Decimal 15. And that decimal 15 can be identified easily because 2 power 4 is 16, minus 1 is your 15 decimal. Okay. So if you're having 1, 2, 3, 4 decimals, sorry, 4 bits, you can have a maximum value, maximum decimal equivalent of a 2 power number of digits minus 1 that we have studied yesterday. So 2 power n minus 1. So to represent a 15 decimal, I require 4 digits. Similarly, to represent 254, I'm trying to identify how many digits are required, not in 2's complement representation, a simple representation of 254. So 254 implies 2 power 5 is 32, 2 power 6 is 64, 2 power 7 is 128, 2 power 8 is 256. So 2 power 8 is 256. So if I'm using 8 digits, I can represent 256 minus 1, that is 255. So let me represent 255, simple 255, not in towards representation, nothing like that. Just a 255 in decimal, I'm converting into binary, right? 255 implies all 8 digits are 1. 1, 2, 3, 4, 5, 6, 7, 8 digits are 1. And this 254 is 1 less than that, okay? 255 minus 1 is 254. So 1, 2, 3, 4, 5, 6, 7. The last digit I am putting 0. So you are going to identify a pattern, right? A pattern that represent minus 254. Okay. Then if you're taking 2's complement of this pattern, you should get this number. That is the logic. Okay. Minus 254 implies number is negative. So you are going to identify some pattern here, right? That you are going to represent minus 254 in 2's complement representation. But if you are taking the 2's complement of this, you will get this value, right? And the range of numbers using 2's complement representation is 2 power n minus 1 negative side to 2 power n minus 1 positive side, right? So 254 is greater than, magnitude is greater than 128 and less than 256. So 2 power 8 is 256, right? 2 power 7 is only 128. So 7 digits are not enough. You should go for at least how many digits? 8 digits. 2 power, sorry, you should go for n minus 1 equal to 8, right? So n minus 1 equal to 8. Then only you can include minus 254 in your range. Look at this, minus 2 raised to n minus 1. So 2 raised to 7 is minus 1, 7 is 128, 2 raised to 8 is 254. So n minus 1 should be equal to 8. So n should be equal to 9, right? 9 digits are required. But we are having 1, 2, 3, 4, 5, 6, 7, 8 digits. But you can extend the sign bit here, okay? Sign bit you can extent. So I can use one more one here, right? Then you should write some patterns here. That should be the 2's complement of this, right? So that if you're taking 2's complement of this, you will get this pattern. The other way, if you're taking the 2's complement of this, you will get this required pattern. So let us take the 2's complement of this. Starting from the right extreme, repeat up to you're observing a 1, then complement the individual digits. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. So this was your representation, I guess. Right, let me check that. That was my, right, this was my representation. Right, 1, 1, 2, 3, 4, 5, 6 zeros, 1 0, right, 6 zeros and a 1 0, right, 1, 2, 3, 4, 5, 6 zeros and a 1 0, right? Roshna, is that clear? Right, identify the number of bits required, minimum numbers required, then identify the required magnitude in binary, and then write its 2's complement accordingly. That's it. Okay. Okay. Thank you all. Thank you very much. We'll continue in the next class. Thanks a lot. Thank you for listening me. We'll meet next time. Bye bye.